Hello everyone, my name is Arnav and today we'll be covering the 5th virtual challenge meeting from 2023 to 2024 of the UIL science exam. Today's video will cover the physics section. Before I show you guys the answers and solutions to the question, I would like for y'all to try the exam yourselves. These are the questions from numbers 1 through 7. These are the questions from numbers 8 through 13. These are the questions from number 14 to 18. And these are the questions from 19 to 20. This is all the constants that you will be needing for this exam that are related to physics. The first 3 questions of the exam are the assigned reading questions. So you'll be given your book and you have to get the answers straight from the book. So the answer to number 1 is going to be Galileo Galilei. The answer to number 2 is going to be Joseph Black. And the answer to number 3 is going to be greater than 0. Number 4. These 2 planets are ice giants deep with salty seas. So, they're ice giants. The only 2, if we look at each giant's choice, Jupiter's not an ice giant, that's a gas giant. Jupiter, so because the same thing applies to letter C. And Saturn is also a gas giant. So, the only option we're left is going to be letter D. So the answer number 4 is going to be letter D, Uranus and Neptune. Number 5. The unit of power is the watt, which expressed in terms of SI-based units is what? So we know power is equal to work divided by time. So work is equal to force times displacement over time. And force is equal to mass times acceleration. So you're going to get mass times acceleration times displacement divided by time. So mass is measured in kilograms. Acceleration is measured in meters per second squared. Displacement is measured in meters. Time is measured in seconds. So rearranging this entire fraction, you'll get the SI unit kilograms times meters squared over seconds cubed. So the final answer to this question will be kilograms times meters squared divided by seconds cubed. So the answer would be letter E. Number 6. A falling ball takes 0.422 seconds to travel past a window. From what height above the window was the baseball released? So we're trying to find height above the window. So we know this ball initially had an initial velocity of 0. So we can draw the initial velocity in blue and the acceleration in red. So since it had no initial velocity, it only has an acceleration that is equal to gravity. And we know that is equal to 9.8 meters per second squared. So when it just drops normally, there was no initial velocity. Once it entered the window, right here, the moment it hit over here, right before it enters, it has an initial velocity. So the acceleration is still g, still 9.8, but the initial velocity will say v1. Or, you will say v1. Right as it's about to touch the ground, same thing. Right before it touches the ground, it has an initial velocity v2 with acceleration due to gravity, g. But v2 obviously being a lot greater than v1. I'll just draw that out. v2 being a lot greater. So we know that the height of the window is 2.75 meters. So with that in mind, let's look at the problem. We want to find the height above the window released. And we're given the time, the displacement of the ball through the window, as well as the gravity, because we know that it's on planet Earth, so it's 9.8. So how would we move this, or how would we do this out? We have 2 kinematic equations we can use. Displacement equals initial velocity times time plus 1/2 acceleration times time squared. That's one equation we can use. Or we can use final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. Which one should we use for this case? We're given time, so we should use the kinematic equation that has the time in it, which we know here because it has time. So, plugging in the values. The ball travels through the 22.75 meter window, which we don't know the initial velocity. We know that it took 0.422 seconds. The acceleration to gravity is 9.8, and again 0.422 seconds squared. So this is what we can come up with using the kinematic equation. Solving for initial velocity, so we would get 2.75 minus 1/2 times 9.8 times 0.422 squared, divided by 0.422. The initial velocity of the ball, or actually I'll draw it in V1. V1 is going to be equal to 4.449 meters per second. So now we know initial velocity. We don't want to find initial velocity. We want to find the height above the height the ball was released above the window. So we want to find, I'll draw in green, this height. The height between the ball before it was dropped and the ball once it touched the top of the window. How do we do that? Well, we know the initial velocity before it, through the window. That initial velocity through the window is going to be considered the final velocity in this region up here. Because the ball is in this position, this will be final, this will be the initial. So we use the second equation here. Final velocity squared equals initial velocity squared plus 2AD. In this case, since this ball is considered final position, it is the final, that would be the final velocity. So 4.449 squared. What is the initial velocity? This ball, like I mentioned at the top in the beginning of this problem, this ball has no initial velocity because it's just being dropped. So there's no initial velocity. Acceleration to gravity is 9.8. And we're trying to find D. We're trying to find the displacement. What's the distance between the ball before and after? Solving for D, you're going to get one point zero zero, 1.01 meters. So the answer to number 6 is going to be letter A, 1.01. Number 7. When the 1.2 kilogram block is released, the 2 kilogram block accelerates up on the inclined surface. The angle of inclination is 18.2 degrees and the coefficient of sliding friction is 0.284. Find the tension on the cord, assuming that the pulley is frictionless and massless. So what are we given? We're given the mass of the two blocks. I'll call this one mass 1, this one mass 2 for the sake of my explanation. But I'll plug in the proper values later. For the first step on any of these physics problems, we want to draw out all of our forces. So what are all the forces we have? We have the weight force, which I'll diagram in blue, acting on this block. I'll call that weight 2. We have the weight force acting on this block. I'll call that weight 1. We have tension force coming from both blocks towards the pulley. Tension, and they're the same. They're actually, so there's no tension to 1 or tension 2. And we know there's a friction force that's opposing the motion of this block. So it's going to be a force of friction. These are all the forces on the block. And also one more thing, this is not necessarily a force, but now we want to diagram the net force. This is going to be net force, which is equal to the mass times acceleration. So in this case, mass 1 times acceleration. This, I'll draw it over here. Net force equals mass 2 times acceleration. So net force is just the combination of all the forces. Remember, so it's not necessarily something we're adding in, it's like combination of everything. How do we add all these forces here? We can actually break this weight component into two different arrows. This component over here, we can break it into two different arrows. One going like this, and one going like this. We're given the angle of inclination, which I'll draw in green. This angle of inclination is 18.2 degrees. Because of similar triangles, this angle right here in green, that's also 18.2 degrees. So these two angles are equal. These two angles are equal. So if we copy that triangle down, we have this side length here equals weight 1, and we have a right triangle down. You have this angle, 18.2 degrees. So because of trigonometry, this one will be weight 1 sine theta, and this one will be weight 1 cosine theta, where theta in this case is 18.2. So we can break that, we can remove this blue arrow, replace it with the two black arrows. This black arrow is parallel to this arrow, so we combine those two, and this one here that I just drew, I'll use in red, that's the normal force. That's the weight component that's going to be acted on by normal force, so that cancels out. So you will also, I also forgot to draw this out. You will have, what color should I use? Skirt red. You will have normal force. So normal force and that weight component cancel each other out. So you're left with tension, the horizontal weight component, which in this case was sine theta, and the force of friction. So now we'll draw the equation. The net force in that direction, in the x direction, is equal to tension minus the force of friction minus weight 1 sine theta. So tension, force of friction, weight 1 sine theta. What about in the y direction? That one is just, it's a bit simpler. It's equal to the weight force of the second mass minus the tension. So weight force of the second mass minus tension. So also, what is net force? Remember, according to Newton's second law, net force is equal to mass times acceleration. So the net force of object x is equal to the mass of object x times acceleration. And the net force of object y is equal to mass of y, or actually in this case object 2. Oopsies. So this will actually be m1 times acceleration, m2 times acceleration. So we have these two equations here. Also, another thing, the accelerations are equal because the whole system is attached and moving together. So the two blocks are moving together, so their accelerations are equal. Now we want to find tension. So for now, let's solve for acceleration first, because it's a bit easier to solve for acceleration first than solve for tension. Rearranging the second equation, you can get tension equals weight 2 minus mass 2 acceleration. Plugging this into the first equation, draw that in green, plugging that into the first equation, you'll get mass of 1 times acceleration equals weight of the second object minus mass second object times acceleration minus the force of friction minus the weight of the first object times sine theta. We know weight is equal to mass times gravity, so we can actually replace the weight forces with mass and mass times gravity. This would be m2g this here would be m1g. So let's move this. This would be m1g. Now moving, let's move this to this side. You're going to get mass of 1 times acceleration plus mass of 2 times acceleration equals mass of 2 times gravity minus the force of friction minus the mass of 1 times gravity times sine theta. And now finally, factoring out acceleration, you can get this entire equation, mass of 1 plus mass of 2 equals, this side stays the same. And dividing both sides by mass of 1 plus mass of 2, you can get acceleration equals mass of 2 times gravity minus the force of friction, which actually I should have mentioned that before. Force of friction is equal to the coefficient of friction times normal force. And remember the normal force all the way back here? That normal force is equal to, I'll redraw that. That normal force is equal to the component that it canceled out with. So the normal force is equal to this component here. W1 cosine theta. So, and we know W1 is just mass of 1 times acceleration. So force of friction is equal to coefficient of friction times mass of the first object times gravity. Because normal force and mass of 1 times gravity times cosine theta. Just rearrange that, yeah. So we can move that down. Coefficient of friction times the mass of the first object times gravity times cosine theta minus mass of 1 times gravity times sine theta over mass of 1 plus mass of 2. So now we got our entire equation. We know all these values. We know mass of 1 is equal to 2 kilograms. Mass of 2 is equal to 1.2, gravity is equal to 9.8, and theta is equal to 18.2 degrees. So plugging everything into our calculator, we'll get 1. Oh, so the coefficient is 0.284. So coefficient of friction is equal to 0.284. You're going to get acceleration to be equal to 0.109 meters per second squared. That's our acceleration. But we want to find tension on the core. So we look at this equation that we made all the while back in the brown box. So tension is equal to weight 2, which is just mass of 2 times gravity, minus mass of 2 times acceleration. This is just plugging in. Mass of 2 is 1.2, gravity is 9.8, and we found using the acceleration, we found the answer. We're going to get a value of 11.629 newtons. So the answer to this question is going to be C, 11.6. Number 8. An alpha particle with a mass of, let's round that to 4, with a mass of 4 AMU traveling at 4.88 times 10 to the 5th meters per second has an elastic head-on collision with a neutron with a mass of 1 AMU, rounded. The neutron was at rest before the collision. Find the speed of the alpha particle after the collision. So find the speed of the alpha particle after the collision. So this question relates to the momentum and conservation of kinetic energy as it's an elastic collision. So let's first use the conservation of momentum. The law of conservation of momentum states that the total amount of momentum before the collision equals the total amount of momentum after the collision. quick recap, momentum is equal to mass of an object times velocity of the object. So the total amount of momentum before the collision. So the collision is between the alpha particle and the neutron. So what's the momentum of the alpha particle? What's the momentum of the neutron? The momentum of the alpha particle before the collision plus the momentum of the neutron before the collision has to equal the momentum of the alpha particle after the collision plus the momentum of the neutron after the collision. What is the momentum of the alpha particle before the collision? So the mass of the alpha particle before the collision was 4. And normally mass is written in kilograms, but in this one case we can write AMU because everything is going to be written as AMU, so everything cancels out. So the mass of the alpha particle is 4. The velocity of the alpha particle is 4.88 times 10 to the 5th. That's the velocity before the collision. The mass of the neutron before the collision is going to be 1. And the mass of the neutron after the collision, we know the mass of the neutron before the collision, the neutron was at rest. So that means the velocity of the neutron after the collision, before the collision, is 0. So 1 times 0 is just going to be 0, so we don't need to write that. What's the momentum of the alpha particle after the collision? So right here. The momentum of the alpha particle after, so the mass of the alpha particle after the collision stays 4. But what is the velocity of the alpha particle after the collision? That's what we're trying to find. So we leave this as VA, velocity of the alpha particle. And what about the momentum of the neutron after the collision? So what's the mass of the neutron? That's just 1. And what's the velocity of the neutron? We don't know that either. We'll write that as Vn. So rearranging the terms and writing that as a linear equation, you would get something like this. You would get 1.952 times 10 to the power of 6 equals 4VA plus Vn. So this is the first equation. There's a second equation we can make. Keep in mind that the question did state that the collision was elastic. What does elastic mean? Elastic means that the total kinetic energy before equals the total kinetic energy after. The total kinetic energy before equals the total kinetic energy after. And we know the formula to find kinetic energy is equal to 1/2 times the mass times velocity squared. Mass in kilograms, velocity in meters per second. So we want to find the kinetic energy of the alpha particle before the collision, kinetic energy of the neutron before the collision. That equals to the kinetic energy of the alpha particle after the collision plus the kinetic energy of the neutron after the collision. So what's the kinetic energy of the alpha particle before the collision? So 1/2 times the mass of the alpha particle is 4. The velocity before the collision is 4.88 times 10 to the power of 5. What about the kinetic energy of the neutron before the collision? The mass of the neutron is 1, and the velocity before the collision is 0. So this can be completely eliminated. What's the kinetic energy of the alpha particle after the collision? The mass after the collision is 4, and the velocity after the collision is VA. What's the kinetic energy of the neutron after the collision? The mass of the neutron is 1, the velocity of the neutron is Vn. So this is the equation you can get from that piece of information. Now let's write that as simplified as possible. We can first cross out 1/2 to both sides because you can multiply both sides by 2. You would get 4VA squared plus Vn squared equals 9.526 times 10 to the power of 11. This is your second equation. So let's bring our two equations down. And what can we do with these two equations? We have two methods as to how we would use these two equations. We can either use substitution, and let's just say substitute. We can either use substitution, where we do Vn equals 1.952 times 10 to the 6th minus 4Va, where we just subtract Va to both sides, and then plug Vn in here so you can get a quadratic. Using difference of squares, you can find Va. That is definitely a feasible method, but it takes too long. First of all, that setting the whole quadratic up can take a while, and it's also very easy to mess up. It takes one wrong button on the calculator for you to waste all that time. I'd say a better way would just be, a better way is just to simply plug in values into the equation. By plugging values, I mean plug in the answer choices that were given. So these three numbers, starting from A, and just keep plugging in until eventually you find a pair that perfectly matches. That may seem long, but with it's just two equations. It wouldn't take too long if you can type well on the calculator. So we know VA. Let's take answer choice A. If VA equals 289,000 meters per second, what would Vn equal? Using this formula, let's plug that in. So VA is 289,364. Vn would equal 796,000 meters per second. So using these two numbers, we got that from the second equation. Let's use both of them and plug that into the first equation. See what we get. If we plug both numbers into the first equation, you're going to get 9.677 times 10 to the power of 11 equals 9.526 times 10 to the power of 11. Obviously, these numbers do not match. And while they are close, we want to find the numbers that they should be almost exactly matching. If we didn't round too far off, we rounded 3 decimal places most of the time, they should not be this far off in terms of rounding. So answer choice A is probably not the answer. But let's look at the other answer choices. Let's say the initial final velocity is answer choice B, 292,000. So that means there would be a new neutron mass, and you would get a whole new number here. So if the velocity of the alpha particle is 292,000, using the equation right here, let's calculate the velocity of the neutron. The velocity of the neutron would be 784,000. Plugging both numbers into the top equation, what you're going to get? You would get 9.526 times 10 to the power of 11. Both the left-hand side and the right-hand side match up perfectly, so B would be the answer to number 8. If you had tried letters C, D, and E, none of the answer choices would have worked. And if you had done the quadratic method, it would have led you to answer choice B. So the answer to number 8 is going to be letter B. Number 9. At what minimum speed must a roller coaster car be traveling when upside down at the top of a circular section of the track if the passengers are not to fall out? The diameter of the circle is 18.2 meters. So we want the car to be at a certain speed so that it can actually maintain the minimum speed where it can actually maintain the loop of the circle. So what are all the forces that act on the car when it's on the loop? When it's on the bottom of the loop, there's going to be weight force pointing down, and there's going to be normal force going up. So we can draw normal force and weight force. When it's on the side, weight always points down. Remember, weight is always going down. Normal force is always perpendicular to the surface. When it's on the top of the loop, weight goes down and normal force goes down. When it's on the side of the loop, weight goes down and normal force goes to the side. But we know if the car at the minimum speed when the roller coaster is just about to detach from the circle, we could say that when it's just about to detach, there is no normal force because the car is essentially detached from the surface. Because this is essentially the minimum speed. This is anything higher and the car will have some normal force on it. So the car will actually detach, and hence normal force, so Fn, normal force, will equal 0. So at the top, what's the net force? At the top of the, I'll draw in red, net force. At the very top, only weight is the force that's acting on it. If the car has been going minimum speed. So this red arrow is net force. So we know net force equals weight plus normal force. And like I said before, normal force equals 0 because the car is at minimum speed. If it was any lower, the car would completely detach and there would be no normal force at all. And minimum in this case we consider as literally just about to detach, the speed right before detaching. And we also know that net force in a circular diagram is equal to centripetal force. Centripetal force is equal to the formula mass times velocity squared divided by the radius of the circle. So we could rewrite this as mass times velocity squared divided by the radius. Weight can be written as mass times gravity. So cancel out mass to both sides, you're going to get V equals the square root of GR. Square root of 9.8 times 9.1, because the radius of the circle is 9.1. So plugging into the calculator, you'll get a minimum speed of 9.444 meters per second. So the answer to this question, number 9, is going to be D, 9.44 meters per second. Number 10. A 0.5 meter long organ pipe is open at one end and closed at another. Find the frequency of the second overtone if the air temperature of the pipe is 20 degrees Celsius. So we have a pipe. It's open on one end and closed on the other. So what are some important formulas we want to know for this? For an open closed pipe, the wavelength is equal to 4 times the length of the pipe divided by the vibration number. So wavelength, which is So let's get the units down. Wavelength has to be in meters. Pipe length has to also be in meters. And L has to be the node number, essentially. Or there's like overtone number, pretty much. So in an open closed pipe, you would start with the so N would be the fundamental. It would start with the fundamental. The first overtone would be 3, the second overtone would be 5, the third overtone would be 7, and so on and so forth. This is for an open closed pipe. So OC pipe, open closed. For an open pipe, and the first overtone would be 2, the second overtone would be 3, third overtone would be 4, and the fourth overtone would be 5, and so on and so forth. This would be an open pipe. But in this case, it's an open closed pipe, and the second overtone would be here, because this is the bass, this is the first overtone, that's the second overtone, so 5. So in this case, N would equal 5. And we know the length is given as 0.525, so the wavelength is equal to 4 times 0.525 divided by 5. The wavelength equals 0.42 meters. That's the wavelength of the standing wave. Get that in red. But now we want to find, what are we trying to find right here? We're trying to find the frequency. So we know velocity of a wave is equal to the wavelength divided times frequency. We know the wavelength, we want to find frequency. That's velocity divided by wavelength. What's the speed of sound in a pipe? Oh, actually, what's the speed of sound in 20 degrees Celsius? Speed of sound can be found through this formula. 0.6 t plus 331. So, where t is temperature. So I'll actually write that as capital T. 0.6 times t, capital T, plus 331. So in this case, the speed of sound is going to be 0.6 times 20 plus 331, which means the speed of sound is 343 meters per second. So plugging that in, 343 divided by 0.42 is going to be equal to 817 meters per second. So the answer to this question is going to be E, 817 hertz. And yeah, complete wrong unit. Frequency is going to be in hertz, not meters per second. So the answer to number 10 is going to be E, 817 hertz. Number 11. Water at a gauge pressure of 4.64 atm at street level enters a building at a speed of 0.922 meters per second through a pipe with a diameter of 6 centimeters. The pipe tapers down to a 3 centimeter diameter at the top floor, which is 24.4 meters above the street. Find the gauge pressure on the top floor. So essentially, we'll draw the diagram out like this. Water flowing through a diameter of 6 centimeters flows at a rate of 0.922 meters per second. It goes up and tapers out into a thinner pipe, which has a diameter of 3 centimeters. So initially, well, I'll draw the radius instead. The radius is 3. The velocity is 0.922. So the radius 1, velocity 1, and the height 1. Since it's at street level, it's going to be the initial height's going to be 0. So that's what's true for the left side. What about for this area right here? The radius of that circle is going to be 1.5 because here it says the diameter is 3. So it, actually wait, not 1.5. Yeah. Pipe tapers down to a 3 centimeter diameter. So the radius of the second circle is equal to 1.5. But what would the velocity be? We know this is one formula we'll have to use. The area of the first cross-section times velocity flowing through the cross-section equals the area of the second cross-section times the velocity flowing through that cross-section. So the area of the first cross-section is going to be pi r squared. So pi times 3 squared. The velocity flowing through the cross-section is 0.922. The area of the second cross-section is going to be pi times 1.5 squared. And we're trying to find the velocity of the second cross-section. So plugging everything in, this is what you would get for velocity. The velocity flowing through the second cross-section is going to be 3.688 meters per second. What about the height of the second circle? That's given to us. It's 24.4 meters above the surface. So now you have everything you need. You especially need these two for the next step. Also, before that, another thing, we want to find the pressures on both sides. So the pressure on the left side is 4.64 atm. What about the pressure on the second side? We're trying to find that, actually. We're trying to find the gauge pressure on the second side. So that's one formula we can use to solve this problem is Bernoulli's equation. Bernoulli's equation states that the pressure of the first on one side plus 1/2 times the density of the liquid times velocity of the liquid squared, V1 squared, plus density of liquid times the gravity constant times the height of the first side equals this entire thing for the second side. So P2, P2, P2. Remember, capital P means pressure, lowercase p means density. So what is lowercase p for in this case? Should have done it earlier. P equals 1,000. The density of water is 1,000 kilograms per meter cubed. So that's something I'm going to box out green. The density of water. So I'll write the density of H2O. So just move that. So density of water is 1,000 kilograms per meter cubed. So plugging everything in. What's the initial height on the left side? 4.64 atm. Remember, 1 atm is 101,300 kilopascals. So 4.64 times 101,300, 101,300. That equals 470,032 pascals. That's the standard unit for pressure. So 470,032 plus 1/2 times density times velocity squared. Velocity in the left side is 0.922 plus density times gravity times the height is initially 0. So there's nothing we need for that. We're trying to find P2. So the density of water stays as 1,000. What is the velocity of the water? Shoot, now that I think about it, the two should go underneath the velocity and the height. What's the velocity of the water at the end? We calculated that to be 3.688 squared times plus PGH plus 1,000 times 9.8 times 24.4. So I'll just bring that down here. Plus 1,000 times 9.8 times 24.4. So now this is the whole equation we have here. We want to find for P2. So solving for P2, the left-hand side would be equal to 470032 plus 0.5. This would equal to 457.042 equals P2 plus 245920.672. This is the equation you will get. So with this equation, now we want to solve for P2. So subtracting from both sides, you'll get 224,536.37 pascals. Converting pascals to ATM, you would divide by 101.300. So remember, so divide by times 101.300 pascals per 1 ATM to get 2.216 ATM. That's the pressure, that's the gauge pressure on the second side. That would be the answer. So 2.216 rounds closest to 2.22. So the answer to number 11 is going to be A. Number 12. Find the voltage drop across the 80 ohm resistor. So we want to find the voltage drop that this resistor contributes. So remember Ohm's law, voltage equals current times the total resistance. Let's try to find the total resistance with all these four resistors. This resistor here, 80 and 120, they're series. So the total resistance is just the sum of these two resistors. So 80 plus 120 is going to be 200. So we can replace this with one resistor that has 200 ohms of resistance. These two resistors here are parallel, so we use the reciprocal rule. 1 over 200 plus 1 over 200 equals 1 over RT. RT in this case would be equal to 100, so we would erase that and we would make this straight line with one resistor of 100 ohms. Now these two resistors are in series, so you can combine these two to make one resistor of 260 ohms. So you can combine these two, 160 plus 100, combine them to make a value of 260 ohms. Now you have a voltage of 40 and a resistance of 260. So the voltage is 40 equals current times 260. the current flowing through the circuit is equal to 40 divided by 260, which is 0.154 amps. So that's the current flowing through the circuit. Now we know the current, let's get everything out for a second. Maybe a sec. So let's just unravel everything. We know the current flowing through, I'll write the current in green. Current of 0.154 starts here. It flows through this resistance. It's series, so just the full current flows through here. Now you lead to a parallel resistor, a parallel circuit, where this is 200 ohms. So we could replace this part with one resistor worth 200 ohms. So now this green is flowing through both of these. When you flow through a parallel circuit, the current is inversely proportional to the resistance. But in this case, since both resistances are equal, the current is split perfectly in half between the two. So 0.154 divided by 2, the current through this side will be equal to 0.077. The current through this side would be equal to 0.077. So it's perfectly split. Now if we unravel this, a current of 0.077 ohms is flowing through both of those resistors. And since it's series, the current does not change between the two. So the current flowing through the 80 ohm resistor is 0.077 amps. Voltage, remember the formula, voltage equals current times resistance. Current is equal to 0.077. Resistance is 80. The voltage drop here would be equal to 6.154 volts. So the final answer is 6.154, or A, 6.15 volts. So the answer to number 12 is going to be A. Number 13. Consider a square with each side length equal to 75.8 centimeters. There is a 6.92 microcoulomb charge placed at 3 of the corners. If the magnitude of the net electric field, what is the magnitude of the net electric field at the other corner? So we need to know a couple of formulas for this question. The formula to find electric field is equal to the electric force divided by the charge on the point. And we know the formula to find electric force is Coulomb's law, where it's Coulomb's constant times the first charge times the second charge divided by the distance between the charges squared. So plugging this value into the first equation, you will get Coulomb's constant times the first charge divided by the radius squared, by the distance squared. So that's the formula to find electric field. So let's say you have a square. And you have at 3 points a charge. Each charge is 6.92 microcoulombs. So 6.92 times 10 to the power of negative 6 coulombs for all 3 of these. So with that in mind, we want to find the net electric field at this point. So using this formula, we know Q for each of these charge. Q is a charge, so we know Q for each of these. And what about K? K is a constant. It's called Coulomb's constant. It's located on your formula sheet right here. Coulomb constant. So you know Coulomb's constant. And we know R too. But you guys have to realize that electric fields are vectors. They're not scalars. So what does that mean? So this first point generates this. Actually, now that I think about it, I'll do it in different colors to make it easier to see. The first point generates a field going this way. The second point, and since it's a positive charge, it generates outward fields. The second point generates a field going this way. The third point generates a field going this way. Why is that, you at? Positively charged electric fields, we know this is positively charged because there's no negative sign here. They generate electric fields outwards. So that's why the arrow is pointing outwards. So that's true for all of them. Each electric field generates one that's out. Each charge generates an electric field pointing outwards. So our goal is to add these three vectors. Let's first find the values of the three vectors. You use that by using this equation. So let's try to find the value of the green vector. So E and the electric field equals Coulomb's constant times the charge divided by the radius squared. And we know each side length of the square is equal to 0.758 meters for each side length. So plugging that into this equation, you can get Coulomb's constant, which is 8.99 times 10 to the power of 9 times the charge of the green point, which is given 6.92 times 10 to the power of negative 6 divided by the radius, or the distance between the point and the corner, which are given as 0.758 squared. Plugging all these values into a calculator, you can get an electric field of 108,274.8 newtons per coulomb. So that's the electric field. That's the electric field for this green arrow. And guys, if you guys look carefully, you'll realize that the charge on the brown point is the same as the charge on the green point, and the distance between the brown point and the blue point is the same as the distance between the green point and the blue point. So the charge of the electric field on the brown point is the exact same as the electric field on the green point. So both of these have the same electric fields right here. But what about the red now? The charge on the red point is the same, but the distance between the red point and the blue point is not. If we use the Pythagorean, the 45, 45, 90 triangle, this would be x, that would be x, this would be root 2x. Using that, we know the distance between the red and the blue point is going to be 0.758 times the square root of 2. You can also use Pythagorean theorem here. Just if you find these two lengths, you can find the hypotenuse of the triangle. So that's what R is going to equal. So using our second electric field formula, K stays the same. Q also stays the same, 6.92 times 10 to the power of negative 6. But R is what changes. So this squared. So plugging all this into a calculator, you're going to get a value of 54,137.398 newtons per coulomb. So that means this value here, copy, translates over here. I'll just remove newtons per coulomb for here. So now what do? We have the three vectors. Now we need to know how to add vectors. When we're adding vectors, we take the tip of one vector, like the base of one vector, and add it to the tip of the other vector, like that, like what I did with the green arrow. The base of the green arrow is being aligned to the tip of the brown arrow. And when you add vectors, you find the distance between these two lines. So you find the distance between the base of the other and the tip of so base of the brown arrow, tip of the green arrow. That's how you add vectors. And since these two vectors are parallel to each other, we can just add the numbers normally. So let's do that. If we did this between the green and the brown vector, what would we get? We would get a right angle. We can get a right triangle. Brown. So, with this in mind, the brown leg, which remember is going to be the same value right here. Both legs will be this value. What would the hypotenuse be if this is a right triangle? The hypotenuse just the same as this number times the square root of 2, because this is a 45, 45, 90 degree triangle. So the hypotenuse is 153, 123.680. 685. So that's the hypotenuse of the triangle. 153, 123.685. So now when you add these two vectors, you can get this black vector that I just drew. And you want to add the black and the red vectors. So we just got the black vector. Plus, what was the red vector? We got that as 54,137.398. Add these two values together. You're going to get 207,261.083 newtons per coulomb. So the answer to the question is 207,216, or closest to letter C, 207,000. So the answer to number 13 is going to be letter C. Number 14. Consider the iron core solenoid that is 32 centimeters long, 1.4 centimeters in diameter, and has 400 turns of wire. The iron core is made from the iron with a relative permeability of 2400. If the current of 0.5 amps flows through the wire, find the magnitude of the magnetic field produced. Let's draw the situation out. You have wire flowing through these loops. There's 400 loops. And you have an iron rod placed between the wires with a diameter of 1.4 centimeters. So, and there's a current going through this. There's a current flowing through the rod with, and it flows through the wire too. So if the current flows through the wire, so this electrical current that's flowing through the wire, it has a current of 0.5 amps. So with everything in mind, let's write out the formulas and to find the magnetic field produced from this wire. The formula to find magnetic field of a solenoid is the permeability of free space times the current flowing through the wire times the number of coils divided by the length of the wire. But this is to find the permeability through a vacuum. But we know in this case there is a relative permeability. And to find the relative permeability, the formula for relative permeability is relative permeability equals the permeability through the object, so I'll just try permeability through a medium, divided by the permeability through a vacuum. So in this top formula, we're actually going to replace that with the permeability of a medium, because we know that there is relative permeability out there, which is 2400. So to find the permeability through the medium, that's the relative permeability times the permeability through free space. We know the relative permeability is 2400, and we know the permeability of free space is a constant given to us on the formula sheet. Permeability of free space. So with that in mind, plugging that into a calculator, we can get 3.01 times 10 to the power of negative 3. That's the new permeability through the medium. So permeability through the medium. Plugging this into this formula, we can get the current flowing through the wire is 0.5 amps. The number of coils is 400. And the wire is 32 centimeters long, or 0.32 meters long. So plugging everything into the calculator once again, you can get the permeability through the object is equal to, in this case, I'll just say permeability through the medium, magnetic field through the medium. So the magnetic field through the medium is going to be equal to 1.885 teslas. So the answer to the question is 1.8, is closest to E, 1.88 teslas. Number 15. A loop with an area of 400 centimeters is positioned perpendicular to a uniform magnetic field. Without changing the direction of the field, the magnitude of the field is increased from 22 microteslas to 88 microteslas in 1.6 milliseconds. Find the magnitude of the average induced EMF in the loop. So we have a loop with a magnetic field going through it, and all of a sudden, like, the magnetic field strength is increased from 22 microteslas to 88 microteslas in 1.6 seconds. That generates a current in the wire, and that current has a certain voltage. That voltage is what's known as the average induced EMF. So to calculate this voltage, we write it as epsilon. That's the average induced EMF. It's equal to -1 times the number of coils times a change in magnetic flux divided by the change in time. So this is average EMF. N is number of coils. In this case, N is just going to be 1. This symbol here is change in magnetic flux. And this here is going to be change in time. So we know the number of coils. That's just going to be 1 because it says a loop. So it's just 1 coil. And we know the change in time is 1.6 milliseconds. What is change in magnetic flux? To find change in magnetic flux, you find the change in magnetic field times the area times cosine of theta. What is theta? When you draw a line, when you draw a green line perpendicular to the coil, theta is the angle between the green line and the magnetic field. So in this case, there is no, the angle between the green line and the magnetic field is going to be 0 degrees. So that means, so that stays the same. So that means change in BA. Because cosine of 0 degrees is just 1, and BA times 1 is just BA. So magnetic field times area. So we know it's magnetic field that changes, 22 to 88 microteslas. So that's equal to final, so we should pull it down. So that means that's just change in magnetic field times the area. So the magnetic field is from 88 microteslas to 22 microteslas. And the area is 400 centimeters squared. We want to convert that into meters squared. Because remember, area is standard, meters squared. Magnetic field is standard in Teslas. So 400 centimeters squared times, we know there's 10,000 centimeters squared in 1 meter squared. So plugging everything in, the change in magnetic flux will be equal to, hold up. Change in magnetic flux will be equal to 0.00264 Webers. This is a change in magnetic flux. Plugging this formula into the top again, what are we going to get? Average induced EMF is equal to -1 times 0.00264 divided by 1.6 milliseconds. So plugging that into the calculator, you can get 1.65 volts as the average induced EMF. So the answer to number 15 is going to be B, 1.65. Number 16. A converging lens with a focal length of 24 centimeters is placed 36 centimeters to the right of a 2-inch tall candle. A second converging lens with a focal length of 48 centimeters is placed 60 centimeters to the right of the first lens. How far is the final image from the candle? So, we have two different images we're going to be creating. The first image is through this candle. We'll get an image. And the second, we'll use that image that's going to be reflected by this lens to create one final image. That we want to find the distance between that final image to the candle. So let's try to find the initial image through this candle over here. We know the focal length of the candle is 36 centimeters, and the focal length of the candle is 24 centimeters. The focal length of this candle is 48 centimeters, and the distance between these two is 60. So using the formula, 1 over the focal length equals 1 over the image distance plus 1 over the object distance. In this case, I'm doing it for the first image. So 1 over 24 equals 1 over di1 plus 1 over 36, because the distance between the candle and the lens is 36 centimeters, and the focal length of this lens is 24. Solving for the first image distance, you're going to get the distance from the first image and the lens is 72 centimeters. So the first image is going to be, I'll draw in green, 72 centimeters away from the candle. So this is the image. So now this image is going to be reflected through this lens. So what is the distance between this image and the lens? Since the lens is 60 centimeters and from this lens, and the image is 72 centimeters, we can consider the distance between the object and the second lens is 60 minus 72. So it's negative 12 centimeters. You don't want to find the absolute value of the difference. You want to find the distance between the leftmost minus the rightmost. So 60 minus 72 is negative 12. So we use the same formula. 1 over the focal length equals 1 over distance between the image plus 1 over the distance between the lens and the object. So 1 divided by focal length, this time the focal length is 48. the distance, we're trying to find the second distance between the image and the lens, and we want to find, and we know the distance between the image and the object is -12. So solving for the di2, distance between the second image and the lens, you can get 1/48 plus 1/12. 1 divided by that, you would get 9.6 centimeters as the distance between the final image, I'll just draw in red, and the lens. So this distance is 9.6 centimeters. You want to find, what are we trying to find? We're trying to find the distance between this image and this final red line. So we can get that to be equal to, and this is actually the other way, one sec. The red image would be over here, 9.6. So we can get, the answer would be 36 plus 60 plus 9.6, because we're trying to find the distance between this candle to that image. So 36 plus 60 plus 9.6, you would get 105.6 centimeters, which rounds up to 106 centimeters. So the answer to this question is going to be C, 106. Number 17. Consider a space station that is 120 light years from Earth. A spacecraft leaves Earth and heads towards the space station at a speed of 0.975 times the speed of light. How long does it take the space station to reach the spacecraft to reach the space station according to the people on the spacecraft? So this relates to time dilation. Time dilation states that the actual time that the space station takes to, like the spacecraft takes to reach the space station, is different from the time observed by the people on the spacecraft. So we know the actual time, we know the distance, and we know the speed. So time equals distance over speed. So I'll have to write velocity just in case. And you might be confused with the 120 light years and 0.975. 120 light years is how, a light year is essentially how far light travels in 1 year. So 120 light years means light has to travel 120 years. That's how far the distance is, if light traveled for 120 years. So we know the speed of light is 3 times 10 to the power of 8 meters per second times 120 years. We don't need to focus on the seconds, because like 120 years, we can focus on 365 days, 24 hours in a day, 60 minutes an hour, and 60 seconds in a minute. That's the distance that the spacecraft traveled. But we also want to, and this is the speed it traveled at. C is equal to 3 times 10 to the power of 8. So this is how much it traveled in meters per second. I mean in seconds. But we don't want to find in seconds. We want to find the answer in years. And we know 1 second, we want to convert this into years. How many seconds is in a year? Well, there's 365 days in a year. There's 24 hours in a day. There's 60 minutes in an hour. And there's 60 seconds in a minute. So we can cancel all these out. So this would be in seconds. This would be in seconds. So you can get rid of this entire side. And you're going to be left with this. 120 divided by 0.975. years. So that means the time it took for the spacecraft to reach the space station is going to be 123.077 years. That's how long it took for the spacecraft to reach the station. But that's not the observed time. That's the actual time. We want to find how long does it take the spacecraft to reach the space station according to the people. They experience a different time because they're traveling on the moving spacecraft, moving near the speed of light. So, according to the speed of the people, let's draw the time dilation formula. Time dilation formula states that the actual time taken from an object moving near speed of light is equal to the observed time by members on that spacecraft divided by the square root of 1 minus the velocity of the spacecraft squared over the speed of light squared. T is actual time. TO is observed time. So plugging everything in, we know the actual time it took for the members on the spacecraft is 123.077 years. The observed time is what we're trying to find out. 1 minus, and if we look here with the radical, v squared over c squared. So I'll make this bigger. 1 minus, what is v and what is c? The velocity of the spacecraft is 0.975 c. So we square that, divided by c squared. So we know c squared and here would cancel each other out. So you're only going to be left with TO over the square root of 1 minus 0.975 squared. Now, in solving for TO, if we plug these two expressions together, you would get the answer 27.35 years. So the answer to this question is going to be A, 27.35 or 27.3. Number 18. There are 17 named particles in the Standard Model. The last 3 particles discovered were the top quark in 1995, the blank in 2000, and the Higgs boson in 2012. So this one, you just have to know your history with the Standard Model. The answer to this question would be the tau neutrino. The tau neutrino was discovered in 2000. Number 19. The period versus distance from the Sun is plotted above for the 6 planets in the solar system. Use the graph to find the mass of the Sun. So, this graph question, we are given the distance of the Sun and the period in Earth years for these points. So, we're going to need to know a little bit about Kepler's law, Kepler's third law, and not just the relationship, but the entire formula. So let's just say this yellow circle is our Sun, and this blue circle is Earth. We know that the blue circle goes around the Sun, not in a circular shape, but we'll consider this as a circle for now. So there's going to be an attractive force, a gravitational force between the Earth and the Sun. So whenever an object is rotating against around another object, there's going to be centripetal force that's pointing towards the center. So the Earth is experiencing centripetal force. The formula for centripetal force is equal to the mass of the Earth times velocity of the Earth squared divided by the radius. I'll make sure to write on the side the units. So m is mass in kilograms, v is velocity in meters per second, and r is distance between the Earth and the Sun in meters. So this is centripetal force, mv squared over r. We also need to know the gravitational force. Gravitational force is the force between two objects. Two objects with mass, if two objects have mass, they have a gravitational force on each other. Gravitational force is defined as the gravitational constant times the mass of the first object times the mass of the second object divided by the distance between the two objects squared. So G is given as a constant, right there, gravitational constant. Capital M is going to be the mass of the sun, so I'll call this capital M. Lowercase m is going to be the mass of the earth. And R is the same, the distance between the sun and the earth. So they're both forces describing the force between the earth and the sun. So since they're essentially equal to each other in that regard, we can set both of these formulas equal to each other. So with this in mind, what can we cancel out? We can cancel out the mass of the earth on both equations because they're both present on both equations. We're left with v squared equals gravitational constant times mass of the sun divided by the distance between the earth and the sun. So you got that formula. But so now we know we need period. Period is one of the things we need, and we don't have that. We do have distance from the sun. Remember, distance from the sun is essentially r. And we have r in our equation. But we want our equation to have period. So we obviously know G and M. M is what we're trying to find. So our equation obviously has to have M. And G is a constant. So we don't really need to replace that. What about V? We have no indication in the problem that we need to find velocity. So we can actually completely, we want to try to substitute velocity with something else. If you remember the angular velocity formula, you would get 2 pi divided by the period. Because we want to find a formula that has period. And we know velocity is equal to angular velocity times radius. So if we multiply radius to both sides, you can get velocity equals 2 pi r over t, where t is the period in seconds. Remember, seconds is a standard unit for time in physics. So replacing this into v squared, you would get 4 pi squared r squared over t squared equals gm over r. Now, what do we have? We have r on both sides, so we can actually multiply both sides by r. We have t, so now we have the period. And G is a constant, 4 pi squared is a constant, and we're trying to find the mass of the sun. So this is perfect. This is what we need. Obviously, let's simplify it a little bit. So that's canceled out, so you can get 4 pi squared r cubed over t squared equals gm. If we rearrange t squared and gm, we'll get this formula right here. This is known as Kepler's third law. That is Kepler's third law. Remember, you may have heard this reference that the period of a planet is proportional to the distance between the planets. So like let's just say the distance between Earth and the sun is multiplied by 9. The period is going to be multiplied by no. If the distance between the Earth and the sun is multiplied by 27, the period is going to be multiplied by 9. So this is the proportion that we can get from this. But we obviously don't need that in this question. So let's run this back a little bit. What are we trying to find? We're trying to find the mass of the sun. So we're trying to find capital M. So we can actually rearrange m and t squared into, one sec, m there, t squared down here, and then m here. This is the equation we need. 4 pi squared r cubed over g times t squared equals mass. So we're given the distance and the period, which I'll put in t. So we're given the distance and the period. We know 4 pi squared. And we also have G on the formula sheet. Let's plug everything in. So 4 pi squared times the distance between the sun cubed. Let's take any one of these points. I'm going to pick the point over here. So you have at least one known value of 150. So remember, distance has to be in meters. So 10 to the power of 9. 150 times 10 to the power of 9. And cube this because of this symbol here. Divided by G, which, looking at a formula sheet, is 6.67 times 10 to the negative 11 times the period squared. Now, one thing you guys have to make sure is the units. We're given the period in years, right here, in Earth years. We want to convert Earth years to seconds because period has to be in seconds. So, if we look at the point here, this is close to 1. I'll just say this is 1. So, 1 Earth year. How many days are in an Earth year? There's 365 days in a non-leap year. How many hours are in a day? There's 24 hours in a day. How many minutes are in an hour? There's 60 minutes in an hour. And how many seconds are there in a minute? Let's move this equation down here. There are 60 seconds in a minute. This is the period over here in seconds. So 1 year is equal to this many seconds. This many seconds. And we want to square that because it's t squared. So making sure everything is right. Yeah, looks good. Now I'll plug it into the calculator. So 4 pi squared times 150 times 10 to the power of 9 cubed divided by 6.67 times 10 to the power of negative 11. You would get a final answer of 2.01 times 10 to the power of 30 kilograms. So and we want to get the closest number to that. So the closest number will be C, 1.98 times 10 to the power of 30. So the answer to number 19 is going to be letter C. Number 20. American physicist Albert A. Michelson invented the interferometer. It is used to obtain very precise length measurements. How far did the movable mirror in the Michelson interferometer move if 240 fringes of a 640 nanometer light are counted? So, the formula for the Michelson interferometer is going to be the wavelength of the light equals 2 times the displacement of the movable mirror divided by the number of fringes. So calculating this, you would get 640 times 10 to the power of negative 9 as the wavelength. 2 times, we want to find what delta L is, and there's 240 fringes that are being counted. So plugging everything into the equation, delta L would equal 7.68 times 10 to the power of negative 5, which is equal to 76.8 times 10 to the power of negative 6. This is in meters. So 76.8 times 10 to the power of negative 6 meters is going to be equal to 76.8 micrometers. So the answer is 76.8 micrometers, or letter D. And we're finally done with the fifth virtual challenge meet section for the physics section. And if you'd started from bio to chem to physics, you'd be done with the entire exam by now. I hope you guys learned something new from this video, and I would greatly appreciate it if you could like and subscribe, as they would motivate me into making more of these types of videos. If you have any doubts, you have any comments that you would like me to address regarding anything in this test, feel free to put it down in the comment section. I'll be more than happy to respond to it. I hope I can see you guys all on my next video, where I'll be going over the invitational meets.